Alright, so in this video we will go over the rules of inference for the Fitch system of propositional logic, and I am going to talk about the 10 rules of inference, but also don't forget that we have already learned 5 operators, and those operators we will be using. They are negation, conjunction, disjunction, implication, and biconditional implication. Okay, we've talked about those in previous chapters. So let's get into it. I'll start first with a rule of inference called and introduction. By the way, I'm going to go through all 10 in a very short period of time here. I certainly don't recommend you do that with your students. You can probably break this up into 2 or possibly 3 class periods. Some of these are really straightforward and the kids have no problem with them at all. Others give quite a bit more challenge, but even those that are seemingly straightforward require some practice with examples. And so I'm going to recommend for your consideration that you stop maybe about 1/3 of the way through, or possibly 40% of the way through, and give some examples. And I'll be doing that with you as well. But I want to go through on this video all of them. So the first thing that I'm saying is, if I know that phi 1, phi 2, all the way up to phi n, and basically any finite number n of logical sentences are true, then I can say that the conjunction of those finite number of sentences is also true. So if we know a list of n logic sentences are true, and is any finite positive integer, then we can infer that the conjunction of those sentences is also true. Yeah, that's almost too easy, but let me give an example. If we know that wolves prey on rabbits and wolves prey on deer, etc., then we can conclude that wolves prey on rabbits and deer and foxes and other wolves. Sometimes kids say, oh, that's obvious. Yes, it is maybe obvious, but I still want to go through this example. And I want to get kids to understand this. Hey, if we know from some reliable source that the following sentences are true. Who's our reliable source, our informant? It's the biologist or the ecosystem scientist. Okay, those are the 4 sentences right there that we know are true. Then we can infer this sentence right here, which is nothing more than a conjunction of all those sentences. Okay? And elimination. Here's how it works. If we know that the conjunction of n sentences is true, where n is any number, any finite integer, then we can infer that phi sub I is true as long as phi sub I is any one of these n sentences. So we could really make n conclusions based on that. Or actually, there's an infinite number of conclusions we can make, because we could say phi 1 and phi 2 are true, plus phi 1 and phi 2 and phi 3 are true, phi 1, maybe not infinite, but a large number of conclusions. Here's an example. If I know that wolves prey on rabbits and deer and blah, 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 then we know that wolves prey on rabbits, wolves prey on deer, and so forth are all true sentences. Okay, keeping this directly connected to what we used as our example before. This is, in some ways, just the reverse of what we already knew. Again, kids are going to say, this is very obvious to me. Okay. Or introduction. Phi sub I, we know. Then we can conclude the disjunction of any number of sentences with phi sub I is also true. So if we know the logic sentence is true, then we can infer the disjunction formed by that sentence with any arbitrary sentences is also true, provided that the known true sentence, this phi sub I, has to be one of these phi's right here. Then that disjunct is true. Because remember, only one of them has to be true. Concrete example, penguins eat fish, and we can conclude that penguins or ostriches eat fish. The big mistake that people make and students will make is, oh, are you saying ostriches eat fish? No, I'm not. I'm saying that penguins or ostriches eat fish. And that's a different sentence. So we're being very, the logic here, the logical sentences have a precision that English doesn't have. And one of the purposes of this course is to help students recognize that. Okay. Or elimination. This is a little tougher, I think. So let's take a look at it. Okay, so in our premises, we have to have at least 2 sentences, but there can be as many, however many there are. Oh, this should be an n right there. I made a mistake. So this should be, say, phi sub n. Okay, so if we have a disjunction of n sentences, and in addition to that, we have n different implications. So we have to have a disjunction with n sentences. N can be any integer, finite integer. So the disjunction, and we have equally as many implications as there are disjuncts, and each of them has the same conclusion. So notice that this says phi 1 and phi 2. This should say phi n, by the way. These do not say psi 1, psi 2, and psi 3. Each one of these has to be identical. Then we can conclude phi. So what I'm saying here is if we know that a logic sentence formed by the disjunction of n logic sentences is true, so we know this is true, that's just telling us that we know at least one of those sentences is true, maybe more. And we know the implications formed by the disjuncts as the antecedent and another logical sentence as a consequent. That's what those are. By the way, this consequent has to be the exact same consequent in every one of the cases. If we know that, then we can infer that the consequent is true. Let me give an example of that. So if we know that today is Saturday or Sunday or Wednesday, that's the the disjunct. And then we also know if today is Saturday, then there is Mass. We also know if today is Sunday, then there is Mass. And we also know if today is Wednesday, then there is Mass. So notice how here we have 3 different antecedents, Saturday, Sunday, Wednesday, but each consequent is the same, that these psi's are all the same here. They can't be different. If we know that, then what we know is one of those, at least one of those, is true. It's either Saturday, Sunday, or Wednesday. So basically what I'm saying is it's not Monday, Tuesday, or Friday. Okay? What did I miss? Whatever. Monday, Tuesday, Thursday, or Friday. Okay? So if I know that, and I know that on each of those, for each of those sentences, variables in this case, not variable, proposition constant, then one of them is true, maybe more than one, then I know each of those leads to the consequent, then at least one of these sentences will be true. And that means there is Mass today. Okay. If we know from some reliable source, somebody who knows about this parish, all of these sentences are true. Today is either Saturday or Sunday or Wednesday. If today is Saturday, then there is Mass. If today is Sunday, there's Mass. And if today is Wednesday, there's Mass. So what we can conclude, there's Mass. Because we know it's one of those days. Okay, I think this is very abstract, hard to understand, and this makes it much better. At least I think it does. The challenge here is to come up with others, and then challenge students to come up with others. And that's a really good way for you to do a formative assessment of, oh, are these kids getting it? Because if they can create an example similar to mine that's accurate, then they're starting to understand it. Okay, let's look at negation introduction. Yay, what is that? Okay, so I'm going to look at this and say we have 2 premises. We're saying that phi implies psi and phi implies not psi. We can conclude not phi. Why is that? Because if phi is true, then we can conclude both psi is true and not true. And that's a contradiction because remember, a logic sentence has to have a truth value of true or false, but not both simultaneously. So if those 2 sentences are true, the only way that can happen is that phi has to be false. Phi has to be false. So if we know that a logic sentence psi implies a contradiction, then you can infer that phi must not be true. Give a concrete example. If penguins can fly, then penguins eat fish. And if penguins can fly, then penguins do not eat fish. See the contradiction there? I would be concluding both penguins eat fish and penguins do not eat fish simultaneously if penguins can fly. So what do we conclude? Penguins cannot fly. This, I think, again, this is a bit abstract and difficult for a lot of students to get. This, I think, makes it easier. So if somebody came up to you and said, these sentences, you'd say, that's a contradiction. Which one is it? Well, my conclusion is penguins can't fly then. Again, similarly, you should have multiple examples of this and then challenge your students to make up their own examples, allowing you to determine whether or not they're understanding it. Let's look at negation elimination. This is probably one of the simplest, and the kids are like, duh, why do you even have to write this out? I'm saying if it's not true that if not phi is true, then phi is true. If the negation of a logic sentence is true, then we can infer the logic sentence. That sounds like a tongue twister, so let me give an example. It is not true that penguins do not eat fish. What do I conclude? Penguins eat fish. It's like you're doing a double negative. Who would ever say this English sentence? It is not true that penguins do not eat fish. Instead, you'd say penguins eat fish. Okay. So again, if that sentence is true, then we can infer this sentence. Another example of where it would be really helpful for kids to write their own. This one's not too tough, but you can get tongue twisted if you try to do that. Okay, let's do implication introduction. Hey, we've already talked about this one before. In fact, we spent a whole video on this. What we're saying is if psi is provable from phi, then we can infer from that if phi implies psi. So again, if psi is provable from phi, if we assume a logic sentence phi to be true and apply a series of rules of inference to this sentence to infer a new sentence psi, then we can infer the original sentence psi implies the new sentence phi. Important to note, we cannot infer the original sentence phi is true. We do not know that, but we do know that the implication is true. Alright, I have a whole video just on that, and this one, to be fair, really needs a lot of practice. So if we assume today is Sunday, then we can apply some rules of inference to infer there is Mass today. And that means today is Sunday implies there is Mass today. So if we assume today is Sunday and then we have some sort of rules of inference, logical inference, and we then infer that Mass is today, we can then infer that today is Sunday implies there's Mass today. That's what this is saying. Let's do implication elimination. Well, we've covered this one many times, but still, we need to have it. Okay, if we assume that a logic sentence phi implies another logic sentence psi is true, that is to say the implication is true, and we know that the original logic sentence phi, antecedent of the implication, is true, then we can infer that the consequent is true. This is called implication elimination. Here's a concrete example. If today is Wednesday, then there's Mass. Well, today's Wednesday, so what do you infer? There's Mass. Okay, this example really helps kids, and having them write out examples would really cement it. So, given two sentences to be true, today's Wednesday and there's Mass, if today's Wednesday, then there's Mass, and, by the way, today's Wednesday, then you conclude there's Mass. Okay. Let's look at biconditional introduction. This is another one that kids think is really simple and almost too obvious. So if I am told that two implications are true, so if we know that a logic sentence phi implies a second logic sentence psi, and we know the second logic sentence implies the original logic sentence, in other words, we know both directions of the implication are true, well then the biconditional implication is true. Well, that is almost the definition of the biconditional implication, so of course. So if an animal has feathers, then it's a bird, and if an animal is a bird, then it has feathers, becomes an animal has feathers if and only if it is a bird. And that's how we say it. Okay. Really important, though, we're going to have to work with this quite a bit because often people assume that the implication is the same as the biconditional implication, and it's not. So you can have a lot of logical fallacies based on that misconception. And let's do biconditional elimination for our final rule of inference. This one is also pretty easy for kids, but still bears practice. So if we know that the biconditional implication is true, then we can infer that the first sentence implies the second, and we can infer that the second sentence implies the first. In other words, we're just saying both directions of the implication are true. Here's the example. An animal has feathers if and only if it is a bird. So what can we say? If an animal has feathers, then it's a bird. And if it's a bird, then it has feathers. Simple, I think, but warning. A lot of people assume this is true for implications, which it's not.